Anything about the course they want to discuss at all, I'd be happy to answer. Yes. That would be a problem, would it not? Where's the thing? Oh, that'd be part of the problem too. Any other issues while we're at it?
Hello, hello.
Any questions at all? Everybody okay on the homework? I don't think it was terribly difficult. Oh, someone has a question. I like questions. 1F on homework 6. Yes, sir. 1F homework 6. Come on. We are waiting for the projector to light up. What is happening, Starfish County? All right. 1D as well. Yes, sir, Mr. Ethan, sir. All right, so let's talk about these. By the way, we were talking about sequences. That's kind of where we've been. I don't know why I keep getting booted out of Canvas. Oh, no, we got to turn that off. That hurts my ears. Okay, are we good? Good. Is that loaded up? Very nice. I just hit the button. Stop it. There you go. So what was D? Or this is homework 6, right? D and F. No. 1F, 1D. All right, so 1D, this one is so homework 6, number 1D. So you need to integrate this function from 0 to infinity of 1 over 1 plus x squared dx. Now, this one can be long and difficult, or it can be straightforward. You need to take the limit as x goes to infinity of this integral. But don't make this problem more difficult than it has to be, because this integral is just the arctan. Yeah. I can't hear you. This thing is really loud. What? Oh, yeah, it should be. That's a mistake. I don't know what's happening up here. It's very loud. So that's T. And so this integral is elementary in the sense that's just the arctan of x evaluated from 0 to t. And of course, this just becomes the arctan of t. Now, when you plug in 0, the arctan of 0 is 0. So I'm just going to write it like this. And the limit of the arctan is pi over 2. Now, again, this is something that you should know, although I'm not curious. I understand that most students in Calc 2 don't know that. The graph of the inverse tangent and its properties is something that you should know. Now, you might say, well, how am I supposed to know that? You never taught us that. That's what people say. And then I will rebut with, well, you should have learned trig before you got to calculus for one. And you should know what the domain and the ranges of the tangent and the inverse tangent. So if you know the graph of tangent is between negative pi over 2 and pi over 2. That's its domain, which means the inverse would be the opposite of that. And so that's where you get this from. Or if you don't understand that, you go to the graph and you graph the arctan. but that's how you do 1D. Does anybody have a question? I'm not saying it's easy, by the way. I don't mean to pick on you, Ethan. I know you asked a question. So when I say you should know this stuff, I'm not trying to say that in a negative way. What I am trying to do is I'm trying to let you know that these are, see, again, it's worth pointing this out. What makes calculus such a difficult subject to learn is you ain't just learning calculus. You're also learning all the other crap that you were supposed to learn before you got to calculus that you either did learn and forgot or never learned. Does that make any sense? I wish there was a better way for me to say that. Yeah, you could have done it trig sub, but that's like putting an atomic bomb on an ant farm for this problem. So I think what you're suggesting, Ethan, is you wanted to do the trig sub. You could have done that, but what you should remember is you should remember the derivative of arctan is 1 over 1 plus x squared. So the integral is an elementary formula. Okay, that was D. Now, Alex, you asked about F, but F we already did, and F is a hard one. It was on your test. So I broke it to pieces on the midterm. So this integral, this guy converges. And this was your midterm. So if you remember, this is the problem where I said draw some pictures. It's not an easy problem. It's a deep problem. It converges. Why it converges, you can state using calculus 2 information, but the value that it converges to, which we told you last time, is square root of pi over 2. There's no way of showing you that using calculus 2. You need to learn more math. So if you take calculus 3, you'll see the math that allows you to show what the converges to. But the best we can do now is show you that it converges. So that solution, I think we did it in detail last week, actually. I think I did it pretty well. I think I did it in detail. You guys are like, what the hell is he talking about? That was hard. Does anybody else have a question about D or F, problem 1? Yeah? No? What about any of the other problems, 2 through 5 on homework 6? Which one? 2? So this creature, what is there to definitions? You didn't look them up? What? Shame on you. So problem 2 is just, all I want you to do is define these things. So let's just give you a couple hints. Or not hints. I mean, you could Google this. You can read it in the book. So I have a sequence, which I can write. It's generic, so I'll just write it like this. By the way, we can write it in long form. It's this. What does increasing mean? Well, increasing is something like, what would increasing mean? Increasing means where they get bigger, something like 2, 4, 6, 8, 10, 12. Say these are the sequence of even numbers, right? That's increasing. That's the idea. So what does this mean? What is the definition? The definition for increasing means that the term that comes next is always bigger or equal to the previous term. So if you want this in English, previous term is less than or equal to next term. Now, I guess we should be a little more clear. Let me say this more clearly. I'm not going to put less than or equal to. I'm going to put less than, because if we're going to be specific, non-decreasing is less than or equal to. Let's just. Does that make sense? So this has to be true. This has to be true for each index K. It has to be true for 1, for 2, for 3, all the way up to forever and ever and ever. And so the definition of the other ones is similar. So decreasing is defined similarly. You just switch the inequality. Now, the one that it's a little tricky is for us is this idea of bounded. Bounded means you can find two numbers. I'll call one little m and I'll call the other capital M, such that every term is never bigger than one or never smaller than the other. And that's for each K. So here's an example. And we're going to crush on this a little more in a minute. How about this sequence? How about the sequence we've been looking at, sort of? Or we looked at it some, I should say. How about 1, 1/2, 1/4, 1/8, 1/16? This sequence is bounded. You know, for example, 1/2 to the power K is never, ever bigger than 1, and it's never, ever, ever 0. So this is, again, these are some ideas that you have to get out, you have to remove yourself from this systematic math that you're used to doing, all this algebra, all these procedures. You have to use your brain. And I know that's hard for a lot of us, it is. But look at this sentence that I wrote. I mean, that's a loaded sentence. But the biggest number in that sequence is 1, and every term in that sequence is bigger than 0. So that we found two numbers. I found those aren't the only numbers. I can pick other numbers, but those are two numbers. I found them. Well, right. Not just an integer, Zafalgar. It's more than that. K is a positive integer. So this is always true. All right. So does anybody else have a question about problem 2? Now, you might say, why do we care about these terms increasing and decreasing? Well, they're very important from a theoretical standpoint. In fact, you can compare it to this integral. Notice this integral, we couldn't say what its value was, but we could reason that it had to have a finite value. And so one of the things that's going to happen with sequences is we're going to be interested in their patterns. We already told you this. We're going to be interested in adding them up. And one of the important things is we're going to want to know, do they add up? Like we alluded to last week. And the issue is, in most cases, you're going to be able to say, yes, they do add up, but you're not going to be able to tell us what they add up to. But that's okay. So, you know, it's hard for you as a beginning student, one with very little experience, to understand that. But oftentimes the answer we want or hope to find can't be reached. So we do the next best thing. Now, some of you will, you know, I guess maybe you'll notice that outside of math class too, if you ever study certain types of things in like chemistry. I mean, a good example of this is the idea of when we study things like the hydrogen atom, quantum mechanics, and we're we're trying to understand electrons, and we might say, okay, where's this electron at and how's it moving, or what's the energy? And the thing is, those are really hard questions to answer. So we rephrase the question. Instead of saying, where's the electron, or where's it at, or what's its momentum, we say, what's the probability that something happens? Because we can answer that. So oftentimes we have to change the question to get information. And so the first place you guys saw that recently was with integrals. If you look at the on problem 1, there's 6 integrals I asked you to do. The first 5, you can tell me whether they converge or diverge, and you can not easily, because this isn't easy. It's not easy. I hate saying that. I feel like a jerk anytime I say something's easy, right? I've said that twice. I said, Ethan, you should know this. This is fundamental, but I hate saying that because this stuff is not easy. But the first 5 of those integrals are relatively simple, relatively simple computations, and you can determine the exact value. But integral f, in order to determine the exact value, requires some very fancy math that you don't know yet. So the best you can do now is say, it does equal something, I just can't tell you what it is. Of course, you could go and do like numeric integration and give me a good approximation if you wanted. So that's sort of where we're at now. We started this idea of trying to understand infinite sums. And so don't forget where we're at. It's actually worth us pointing that out before we even talk about any other questions on homework 6. So let's sort of round the troops and let's think about that way. So last week, what we did is we asked about what we were calling infinite sums. And that is, if I take a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, how do we even define this? What does this even mean? And remember, we motivated this and what were these examples suggesting? Well, they were suggesting that 1/3 was equal to 3/10 plus 3/100 plus 3/1000, etc. And we also had this example, 2 of them, that suggested this was equal to this. So these were the examples we did last week. We tried to motivate this idea. And what we did, if you remember, is we did a numerical sort of exercise. We took that second thing down there, that 1/2 plus a 4th, and we went to a calculator and we just kept adding them up. And what I hope that you would see is that there was some sort of pattern hiding out. And the pattern is that we were, when we added a bunch up, and then we added more up and then added more, we noticed that there was some sort of list of numbers occurring. And this list kept getting closer and closer to 1. So if you're confused by what I'm saying, you might want to go back and review your notes. But we were generating a list of numbers. And this list of numbers had a property. And that is, they were like getting closer and closer, in quotations, to 1. And I suggested that there was some sort of limiting thing happening here. Does anybody have a comment or a question? Anybody have anything they want to ask or say? Do you want to tell us what you had for breakfast? Do you want to tell us how much fun you had this weekend? It's cold out. The weather sucks, right? We can complain about the weather. You can complain about the fact that your quiz graded you funky. You can have a mutiny and kick me out. Some of you are probably like, it graded me wrong? Yes. Ah, that's a good complaint. Yeah, well, you can see it on Mile of Rose, just not on. What the hell are you worried about that? I know. You. Oh, that's even more important. Yes. Someone did email me about that. You guys are like, I feel like it's unfair because you guys are like the highest class I have this semester. Like, highest. No, you're not the highest level, and I'm treating you like it. I'm such a meanie. You guys should get. Yeah, I apologize. I'm in a boot. What the hell happened to you? Yeah, Josh. See, I was saying that before you got here. I misunderstood the Canvas quiz. I have to fix it. Don't worry, I will fix your grade. Well, that ain't good. Volleyball, bad news. You better rest up. Put some heat on it. Or like Shaq says, what did Shaq always say? Icy hot. All right, that was good. We got out of that. All right, so what was the point of problems? So let's put it this way. So to properly define this business, we first defined a sequence. So that's what we did last week. And once we define a sequence, is now we discuss and examine patterns. So let's look at the homework problems. When is the homework due? Is it due already? I forget. Or is it due tonight? Yeah. Hopefully I made you turn it in already, but who knows if I did. It was due October 16th. Perfect. That's even better. Good. That's good. That's good because it wasn't hard, and it's not really right or wrong. Very good. All right, that's good because the reason I ask is I was going to do these problems, but then I don't want you just to write down what I write and then turn it in because there's zero learning happening when you do that. Learning happens when you compare your gibberish to the actual gibberish that I write. Does that make sense? I shouldn't say it. Maybe I write gibberish. Who knows? All right, so let's illustrate. Consider this sequence. The sequence 1 over n, n goes from 1 to infinity. So if we write out the first few terms, you have 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, 1/10. I'm getting bored and I'm running out of space. So the thing I asked you to do on the homework was to describe any patterns. And I was hoping you would use words that you saw on the previous page, like here's some observations. First off, it's decreasing. Why is it decreasing? Well, look at the pattern. The pattern is 1 over k is clearly bigger than 1 over k plus 1. Now, if you're not sure why that's the case, just do the basic arithmetic and rewrite this. It's true because k plus 1 is bigger than k. So I'm relying here on context. I'm relying here on the fact that you guys know that k is a positive integer and that you have fundamental numeracy. That is 1 over 10 is greater than 1 over 11. 1 over 92 is greater than 1 over 93. So what's weird is symbols are a funny thing, because what I've written right here, this is literally middle school mathematics. When you learn fractions, which fraction's bigger? You would have done this like in a 5th, 6th, 7th grade math test. Remember, you'd have these problems where they give you a bunch of fractions and then ask you to list them in order from increasing to decreasing. Who'd have thought that would be important one day? Although it is important when you're cooking dinner and you need to know what's bigger, 1/3 or 2/3, and then you say, no, I don't know, Grady. I just look at what cup is bigger. I don't need the damn number, right? So it's decreasing. And it's bounded as well. Why is it bounded? It's bounded because 0 is always less than 1/k, and 1/k is always less than or equal to 1. So not only am I telling you the properties, decreasing and bounded, I am showing you why. I'm not just saying it's decreasing, I'm providing evidence. I'm giving you logical reasoning for why. Now, of course, you're going to say that's just symbols and I don't understand it. And then I'm going to tell you, I get it. Symbols are scary. Spend more time thinking about it. Does anybody have a question about this? Okay, another pattern I see in, someone has a question? That's logical. And probably most importantly, the pattern I see as is the following. So the numbers seem to be getting close to 0 for large K. You know, for example, a sub 100 is 1/100. Well, what is 1/100? I mean, if you know, if you take a calculator, you know, you move your decimal point to the right 2, this is 0.01. And then if I do like a to the 956, well, that's 1/956. That I can't do in my head. Oh, yes, I can. What am I kidding? I should retire. And so this is approximately, well, let's just write approximately 0.00105. And then maybe I do like a sub 5,600 or 5,064. I'm just making these numbers up, by the way. There's really no method to my madness. And here I get 0.0001975. So the point I'm trying to make is it looks to me like as these guys get large, as n goes to infinity, this looks like it's going to 0 to me. That's a pattern I see. Or I guess I should use K here. I was using K before. It doesn't matter. That's something in my mouth. Does anybody have a comment about this? Question? I'm about to just start giving points to people who have questions. Instead of homework, it'll be questions. You guys are so shy. I hate it. You guys are the opposite of me. You should have seen me in class. I'd be asking anything and everything. I'm getting my money's worth. Okay, so let's look at the next problem on the homework, which was this sequence. So let's take 2n over 3n plus 1. N goes from 1 to infinity. So if we write out this list, the first few, I'm not going to do 10 because my head will hurt. When n is 1, this becomes 2/4. And I know that's 1/2, but I'll write it as 2/4. When n is 2, I get 4/7. When n is 3, I get 6 over 10. And then there's a clear pattern now, I think. 8/13, 10/16, and I'm out of space. Now, this one might not be so clear what's happening. By the way, let me clean this up. I don't know if you realize that's a 3. So it turns out that this sequence is actually increasing. So the first thing I notice is that it's increasing. Now, why is it increasing? What makes me think about that? Well, look at the thing. This one is probably not so clear, but if you just do some basic arithmetic on consecutive terms, you can get some insight for that, but that's not a proof. That's not mathematically sound. So how do I actually verify that it's increasing? Well, this is a little more algebra. I need to show that the kth term is less than the kth plus 1 term. So I have to replace k with k plus 1, and I have to verify this. But this is equivalent to the following. If I do some algebra, that's 2k plus 2, and this is 3k plus 5.
Sorry, it is 2k over 3k over plus 1. It's not 2k over 2k plus 1.
What's that? As a follower, you have a question? I can't hear you.
So it is 2k over 3k plus 1. It is not 2k over 2k plus 1.
I'm sorry, I can't hear you. I don't know if it's my computer or yours.
No. All right, I'm gonna type it.
I have no idea. I don't know if the volume's down. I don't know. Let's see. Maybe turn it on. Okay, you're gonna chat it out even better. No, it's all over 3k plus 1, not just 3k. Huh? Oh, here you're talking about. That is an error. Yes, this is an error. That's an error. Very good. Is that what you were trying to say? That is an honest mistake. Better? Damn. That made me laugh. I was reading this article about teaching, and they were arguing over whether teachers should make errors. Like if they're like, say I was filming a lecture, not live, if I should fix any error. And I'm thinking I make errors on purpose all the time for 2 reasons. 1, because humans make errors. And for 2, sometimes if I actually do make an error, I can lie to you and say that it was an error on purpose, right? See, that works both ways for me. Okay, look, back to this problem. Remember, I need to show that this guy is the kth term, and this guy is the k plus 1. So this is the next term. This is the previous term. I need to show that this is true. So this just comes down to algebra. And, you know, if you multiply this all out or do the algebra however you want to do it, it's 2k times 3k plus 5. That's less than 2k plus 2 times the quantity 3k plus 1. And it's, if you just multiply this out, you can easily see that it's a true statement. Can you imagine if I wasn't? Someone actually once said, they said they think that I was drunk when I taught. Can you imagine? You wish.
It'd be a fun class.
Never. I wouldn't do that to you guys. I wonder why. Hey, Safalgar, not funny. Okay, so what we'd like you to do is again, let me remind you what I'm doing here. I want to show that successive terms in general are following this inequality. What increasing means. It means the kth term is always less than the next term, which is the kth plus one term. And so one way to do this, and this isn't the only way, but this is one way, it's to just show it directly through algebra. I need to show that this inequality is the same thing, equivalent to one that's obvious. And so if you look at the previous problem, this is not, I need to show this is true, and this is equivalent to this. Clearly, if k is a positive integer, k plus 1 is bigger than k. I mean, if you need to go another steps, this is the same thing as 1's bigger than 0. So what I need to do is I need to reduce this ugly thing down to something that's obvious. And so that's what I'm doing. So what I'll do now is I'll multiply this thing out. So if I go to the next page, that thing that I had is the same as 6k squared. And then I have 10k. And I need to now multiply the right-hand side out, which is a little uglier. 2k plus 2, and then 3k plus 1. So 2k plus, or times 3k is 6k squared. Plus, what are the, again, all I'm doing is multiplying this now. 6k squared, and then I have 2 and 6 is 7k. Plus 7k plus 2. Is that? Is it 8? Two. Oh, yeah. 2. No. But 2 and 6, 8k plus 2. Yeah. So that becomes 8k plus 2. Is that correct? Now, if you just subtract the 6k squareds and the 10k's, whatever you want to do, this is the same thing as 2k is less than 2. Yes or no? What's the error here? Now there's an error.
Error is obvious because 2k must be bigger than 2. We made an error when we just...
I know, but where? I know, obviously, but where?
Okay, the previous slide, please. Can you please?
Yeah, but where's the error at? This page or the other page? Right. Where's it at?
Another. It is 2k over... No, God, no.
You talking about right here?
No, it can't be. Give me a sec.
Figure it out.
So
Where's
it is decreasing then. No.
You talking about right here? Yeah. Okay. So this is good. That's the first mistake. Where else? So if we fix that, very good.
It is not increasing. It is decreasing then. No.
Definitely not decreasing. It's increasing.
Yeah. Yes, it's increasing. Yes.
Definitely increasing. So we fix this. This is a 4. This is very good. This is called problem solving. We put a 4 here. I mean, you could see this is, look, the reason I did this, and let me tell you why. Because if you just write out the first few terms, it's going to be increasing. So you know that if you're going to verify it's increasing, that it better work out or something's wrong. So if I put that 4 there, the only thing that changes, by the way, is it only changes this. This is no longer a 10, this is an 8. And now things are obvious and we're excited because I have an 8 on both sides. And that means that this line right here
Robinson was raised here.
is equivalent to an obvious statement, that is 0 is less than 2. So since this is true, we conclude increasing. Now, let me just say one more time, because, you know, of course, someone might say, well, why did you go through all that? Because one of the skills you should have is you should be able to show whether a series or a sequence is increasing or decreasing. This is a skill you should have in calculus. Or let me rephrase that. This is something I could test you on if I wanted to. Something I could assess you on. And there's a couple ways you can do this. I'll show you an easier way in a second. But this is one way. So I need to show this, but I show this is equivalent to an obvious thing, and so I'm comfortable with it. Okay, this thing is also bounded. And that might not be obvious to you. But there are a couple educated things or educated guesses or hints that you have. Even though we're calling this a sequence, you have studied functions. If I replace n with x, you've studied functions before that look like this. In fact, you would have learned long before calculus that if this were a function, y equals 2x over 3x plus 1, you would have learned that that thing has a horizontal asymptote at 2/3. You learned in Calc 1 that that horizontal asymptote occurred because as x goes to infinity, that this expression is tending somewhere. It has a limit. And if you went to your calculator and got exact value, or excuse me, approximating values for these fractions, particularly far out, you would notice something else. And that is, and this is not as obvious as in the previous example, it is bounded. In particular, (2k over 3k plus 1 is always less than or equal to 2/3, and it's always greater than 0. Let's show you why. The 0 part's obvious. I mean, it's a positive number. Well, if I take 2 over 3k plus 1, and I do the same sort of algebra I did in the previous step, this is the same thing as 6k less than equal to 6k plus 1, which is this, excuse me, 6k
I'll think about it.
2. So I multiply this thing out, and this is equivalent to 0 being less than or equal to 2. I'm definitely bounded. Does anybody have a question about this? Now, of course, what I'm doing right now is new to you. Unless you really spent some time over the weekend looking into these things. We didn't do this last week. All we did was talk about a list of numbers. But what I'm trying to do, and I tried to get you to motivate, notice I used the word on the homework, describe any and all patterns. I'm not suggesting that you would write this down the same way I'm doing it right now, but now you know what I'm looking for, what I'm trying to motivate. Okay, so what's even more interesting about this is for quote unquote large values of k, a sub k is approximately 2/3. Let's see that. Let's do what we did in the previous problem. Say like a of 156. Well, that's 2 times 156 over 3 times 156 plus 1. And we can compute that relatively easily on a calculator. I'll use the Google calculator.
We can divide like
Say, you know, Fogger, I can't hear you. What are you saying?
we can divide like 156, like 2 times 156 or 3 times 156 plus 1. We can divide it to
Yeah,
156.
that's what I'm doing. I'm just plugging that into a calculator right now.
It is going to be 2 over 3 plus 1 over 165.
Yeah, but
156.
you don't even have to just do that. You can just go straight forward and get a decimal approximation of it. If I go and just do this math, I mean, just do the number. What do you get? You get 0.66525. And then if I do something like A sub 500, that becomes 1,000 times 1,500 plus 1. And of course, now you're going to get 0.666222. And so the fact of the matter is this goes towards infinity, or excuse me, is n goes to infinity or k goes to infinity. This thing looks like it's going to 0.66666, which we think is 2/3. So the pattern that, again, we're trying to see, can we quantify these patterns that we have? And I'm using arrows because what I'm trying to motivate is there's some sort of limit happening here. And we're familiar with limits, just not these types of limits yet. So perhaps on the next page, I should write this and say it like this. Whoa. So the previous two examples suggest we have a limit. And I'll put that in quotations because it's not the same types of limits that we've seen before, but we might want to write something like the limit is n goes to infinity of 1 over n equals 0, and the limit as n goes to infinity of 2n over 3n plus 1 equals 2/3. Now, if I were to replace these letters n in both of these problems with the letter x, this would look like something we covered in Calculus 1. The only difference is these are sequences, and that means that the variable is restricted to being a positive integer, 1, 2, 3, 4. But that's okay. So what we're saying is, and this is what's really, really cool, is we're going to define the notion of a limit for a sequence. But in most cases, a sequence behaves just, and it's the idea of limits behaves exactly the same as what you were taught in chapter 2 of Calculus 1. And that is limits at infinity. So that's worth pointing out. in the following. So definition. We say the sequence A sub n converges to L. And we write limit as n goes to infinity of A sub n equals L. If we can make A sub n arbitrarily close to L by choosing n sufficiently large. So this is a lot of words, and you don't have to memorize this, and you don't have to stress about it, but that is the definition, and we're going to show you how it's something you've already encountered. I mean, think about the previous examples, 1 over n. I can make 1 over n as close to 0 as I like. I just choose n large enough. I can make 2n divided by 3n plus 1 as close to 2/3 as I'd like. I just choose n large enough. Notice the word converge pops up here. This is the word we used when we were talking about improper integrals. Converge, converge, converge. Go back. So here's a cool thing. It's like we're giving a new name to an old friend. So the question, how to determine limits for sequences. So in general, not easy, but in many cases, we can use our limit laws from Calc 1, since the limit as n goes to infinity of A sub n should be the same thing as the limit as x goes to infinity of some function f of x, if A sub n and f of x have the same formula. So I'm going to show you what this means in a second. Everything we know about functions can apply to sequences in many cases. It's really, really useful. I mean, remember, a sequence is a function. It's just we're restricting the domain to positive integers instead of all real numbers. So I'm going to show you what I mean by this in a second. Again, all these scary symbols seem overwhelming. They don't have to be. You just have to think about the examples that you've done correctly before, and hopefully it will all piece together. Hopefully. No, not necessarily. You don't. So I think your question is, you need to prove that the limit exists? No, I mean, we're just computing it. You can use the limit laws. I'm going to do an example in a second. So let's just do a bunch of them real quick to show you that this is a pretty straightforward task. So the limit, for example, that n goes to infinity of 1 over n should be the same thing as the limit as x goes to infinity of 1 over x, which we already know is 0. Now, you did this way back in chapter 2 of way back in Calc 1. So I'm just going to write down 3 basic examples that we did back in Calc 1. And instead of writing them in terms of functions, we're writing them in terms of sequences. Now, look, there's some subtleties here. This doesn't always work. It only works if the formulas are the same. But for what we're doing in Calculus 2, this is going to work more often than not.
Professor.
Yes.
So when we say limit n to infinity 2n over 3n plus 1, when we say this is equal to 2 over 3, which means this function can never be 2 over 3.
Right. It never spits out 2/3, but you can get as close as you want.
All right. Thank
I mean, think about the graph. Then, you know, your 2x over 3x plus 1 will never, there's no x that will make it equal to 2/3. So perhaps let me show you what I mean. If I go to, where the heck's my internet at? No, that ain't what I want. Give me a second to find, I want a poll. Give me a second here. Let me pull up Desmos. So if I go and I say I graph this function, y equals 2x divided by 3x plus 1. So this is a function you would have studied in Calculus 1 and algebra, pre-calculus courses. Notice that when x is large, this thing has an asymptote. And if you draw the line y equals 2/3, you'll see that that is the asymptote. So that red curve never touches the blue line, but it gets as close as it wants to. It gets getting closer and closer and closer. Now, it looks like it's touching it, but if I zoom in a bunch, you're going to see that it's not. But if I move further to the right, that red curve keeps getting closer and closer to the blue dot. And by the way, it's worth pointing out, and maybe this was the point you were trying to make, Zafalgar. If I go back a few pages to this analysis that I did right here, really, this is not incorrect, but this thing right here can never be equal to 2/3. Try to solve
Right.
it.
Right, that's what I'm saying.
1 equals to 2/3. Try to solve it. It won't make, you can't.
So
Because
I remember
the same
this.
thing I did here, I would get that 0 is equal to 2, but we know that doesn't make any sense, right? That equation has no solutions. So let me be more clear with what I'm saying. I believe your question was the following, Zafalgar, and correct me if I'm wrong. I think your question was, when we write this, like we're writing right here in this middle term, we're not saying that this ever equals 2/3. We're saying it keeps getting closer and closer. That's what we're saying.
Yes, that's what I'm asking. That's what I'm asking. Because previously we said it's smaller and equal to 2/3. So I remember then, and right now I say like it can't be 2/3. You
No,
know.
it can't be. You're right. But it's still not wrong to write less than or equal.
Yep.
It would be wrong to write equals, but it's not wrong to write less than or equals.
Yep. Thank you.
So there's a lot of silver linings here. Most of what we learned in Calculus 1 about limits at infinity and all the limit laws, we can use them to study sequences, and that's good. So it's not like we have to learn a bunch of new things. By the way, a common question that people have is the following: does every sequence have a limit? And the answer is going to be no. Or does every sequence converge? And the answer is no. And the one I gave you on the homework was this. Take this sequence, n starts from 0 and goes to infinity. Get 1, -1, 1, -1, 1, -1, 1, -1. This guy can't converge. And of course, you might say why. And the reason it can't converge is it always alternates between two values. It never gets arbitrarily close to one value. So it can't converge. All right, so here's where we're at. And does anybody have a comment or a question right now about this? Because a couple things need to be pointed out. First off, learning this, especially for those of you who have never seen this before, is difficult. It's a very difficult thing, and it's been difficult when I was a student. It was difficult long before I was a student. It will be difficult long after you guys. If you want to learn this, it takes lots of experience. It takes lots of practice, and you have to expect that you're going to get things wrong. And really, what's even more unfortunate is it's hard enough to understand sequences, and now we're about to step the game up to why we care about sequences to begin with, and that is to tackle these infinite sums. So once again, there's so many things that make a topic like calculus difficult to learn. And then when you put all these difficulties in the context of a class where we have to learn all this stuff in a short amount of time, it really puts a lot of pressure on you, the student. But I just remind you, if I can do it, you can do it. So, you know, that being said, here we go. We can now properly define what we've been calling an infinite sum. So let's do some definitions first. First, we have the following: an expression of the form a sub 1 plus a sub 2 plus a sub 3, on and on and on, which we could write in shorthand notation in the following way: k equals 1 to infinity of a sub k. So an expression of the form here has a name. This thing is called not an infinite sum, but it's called an infinite series or just series for short? So it's interesting. We don't use the word sum here. It's called an infinite series. Okay, so we're giving a name to this. So how do we define this infinite sum? So here we go. We say the series that I just wrote down converges to L, and we write that the sum from 1 to infinity, which again, this is shorthand for a sub 1 plus a sub 2 plus a sub 3. We actually say that this infinite sum, what's called a series, is equal to L if the following is true. If the limit as n goes to infinity, and this is a lot of scary stuff. If this limit is equal to L, we say the series converges, or we say the series sums to L. Woo, scary. So we're gonna break down what this means. This is a very condensed definition, but we can break it down in some simpler form, or simpler terms, so to speak. Before I do that, though, does anybody have a comment, question on this miserable Tuesday? Okay, so let's break this down in the few minutes we have left. So we can break the definition down as follows. So what we're going to do is we're going to add some new numbers. We talked about this last week. We're going to call S sub 1 A sub 1. We'll call S sub 2 A sub 1 plus A sub 2. S sub 3 equal to A sub 2 plus A sub 3. And then in general, say S sub 10 would be A sub 1 plus A sub 2 all the way out to the 10th term. And then S sub n will be A sub 1 plus A sub 2 all the way out to, say, the nth term. So if you think about it, this is what we were doing last week with that series, that sum we started with. So we're going to give a name to this so we can refer to it. We call S sub n the nth partial sum. So to say a series converges, and we can even be more specific, we can say partial sum of the series. So when we say a series converges in English, what that means is the sequence of partial sums converges. That's what it means. So we're going to write that down on the next page, and then we're going to put a bow on this real quick. So to say that A1 plus A2 plus A3, to say this converges to L, this means the sequence of partial sums, which we were calling S sub n, converges to L. So what that means is this limit, which we already wrote, and it's in long form, it's this. Or not long form, in terms of the sum, it's this. So look, this is scary. The notation's scary. The ideas are challenging. They're conceptually difficult. There is no easy way to learn this stuff. It's tough. It's challenging. Most human beings struggle to learn this. I very rarely have met any human being that just gets this. Now, some of you will run into people that understand it, and that's because they've probably seen it before. Hard to learn this. Anyhow, we're out of time. We'll put this in the context of examples on Thursday. Thank you very much. And I will see you guys Thursday. Be safe. And what else did I want to say? That's it. Thank you guys. Appreciate it.